All right, so how did one-pass compilers lead us to invent header files? What did we say? Go ahead.
One-pass compilers, by definition, you go through code once. Multi-pass compilers were super really slow back then, so when they do the one-pass compiler, they have references to things like that.
Okay. So before we had header files, what did we have to do in a situation where we had a one-pass compiler?
Probably declare whatever you're using before you use it. I mean, like in the way that the compiler would compile it, like it has to compile everything that's being declared before it's actually
right. So idea is with a one-pass compiler, we're only going through the compiler itself only makes one single pass through our source code, which means if you have a function down here that calls upon another function that isn't defined till here, that means you need to prototype both of those functions up here so that this guy knows about this guy. All right, so that's really what what we had to do initially was this idea of prototyping. So at the top of your file, you would have basically function headers. Not the implementation of the function, they could be anywhere in the file, but you would have the initial prototype header for the function so that anytime, if this function called upon a guy later on, at least the compiler already knew that that dude existed and what parameters he took for compilation. All right? So the idea was if you had a C or C++ program with a bunch of this crap at the top of it, why not separate that into two separate files? So it's pretty common at the very top of a C program, you'll see just include something.h. All right? That ultimately at runtime gets expanded to whatever's in that something.h, which is going to be a whole bunch of prototype stuff. Right? So what it allows us to do is it allows us to keep our prototypes inside of a header file and then put the rest of the code someplace else. And then at the very top of our program, we only had to reference the one header file that had the prototypes in it. All right, so it kind of invented this idea. Now, once we moved on to multi-pass compilers, where prototyping was no longer required, why didn't header files go away?
They're still useful for bringing in other libraries to your project.
Okay, that's a true statement. So useful for bringing in other libraries. Okay, what else?
They're useful when you're reading through code. You can see like what will be contained in the class.
Okay, so you can look at a header file and get it's almost like an executive summary of what's actually implemented in a actual library, right? Actual code file. So header files, even though they weren't necessary, actually became convenient. They were kind of pretty good idea. So why don't we keep them around? Now the reality is that we've since kind of gotten rid of them. So as a Java developer, we don't use header files. As a Swift developer, we don't use header files. But if you're still writing C, C++, Objective-C things, even though it's not required, header files are still very much the standard. Make sense? So that's kind of the idea of the header file. Okay. And I think I say, okay, go to page 51 in the book. So now we're going to start looking at some code examples. We're going to see if they work on the Mac. If not, I have a Cloud9 account for backup, and we'll see where we can get this stuff to work. All right, I'm going to go. Now, have we actually written like a C program in here yet and seen one run?
That was assembly.
Oh, we looked at the assembly, right? All right, so let's just quickly write a C program just to see it. Looks like I might have one in here. Ah, look, hello world, let's see. So, as an example, here's a call to a header file. So, this is an old C program. So we're including a library, and by us having these angle brackets around this means it's a system library as opposed to something that's local in the directory we're currently sitting in. If it was a local thing, we'd put double quotes around it. So we're including standard io.h. So this is the standard IO library for doing input-output stuff. And now we see, just like Java, all programs begin and end with main. So here's our main method. And in Unix, main returns an int. Well, in C, main returns an int because it was impacted by Unix. Why do you think main returns an int? Go ahead.
So that you can like return different values for whether it was a success or not.
Yeah, like error codes, things like that. We've already seen we've been using commands that commands that pipe into other commands that pipe into other commands. So it might be handy for us to be able to run a Unix command and ask the question, did this guy work? Okay, so Unix commands can optionally return an integer for whether or not it worked, or it could just return an integer for whatever. I suppose you could write a program where main just returns the sum of a bunch of numbers, and as long as you know that's what it's returning instead of trying to interpret it as an error code, that would be fine. All right, so in any case, main returns an int. Parameter for main in Java, main takes in one parameter, a string array, right? Usually called arg, sometimes we call it elephant. But this guy takes in two different parameters. This is an argument count, the number of command line arguments. This is the array of strings. So that's a char pointer argument values. Why is that? Because in C, arrays do not know their length. We have to advertise how many guys are in there. So argc will equal the number of parameters. Char pointer argv, well, char pointer argv, that is, this is an array of char pointers, where a char pointer is a pointer to the beginning of a string. That's how we can think about it. And then we're going to use the printf function that came from standard IO. We're going to print something to the screen, hello world, and then ultimately return 0, the program ended successfully. All right, so that's hello world in C. We'll go ahead and compile that. So we're going to use the GNU C compiler, GCC. And I'll do test.c, press enter. What are you ticked off about? That's interesting. It worked. Must have just had a weird lock file or something. Well, in any case, when I run gcc text.c or test.c, what it did is it generated a file for me called a.out. Okay, this is the standard output file. And a.out, if I do more a.out, it's going to say this is a binary file. Do you want to see it? So this is the output of my my file. That's what my hello world file looks like. Now the reality is, if we were to look at this at the assembly level, because we're actually looking at a binary. So it converted to assembly, then it linked it against the libraries and produced a binary file that ultimately feeds zeros and ones to the CPU. If we were able to look at this, we'd see something along the lines of a hello world program we saw. We were to see it at the assembly level. Okay, so now we're going to go ahead and run this, /a.out. / in Unix, what does that mean? When I say / in Unix, what does it do? / goes back one directory. So / would say go up one directory and then go to a.out. What is /? Yeah, look in this directory. So there, if you look at, here, let me just do this real quick. I'll just run it real quick. So there's our hello world right here. I didn't do a carriage return, so that's it right there. Let's do a quick clear. If I type in ls, let's do ls-a. Notice here, when I do ls-a, it shows me all of the files and directories in this current thing. And anything that has a dot in it is hidden by default. So you would not see these guys. If I just typed ls, you wouldn't see any of those dot ones. But ls-a shows me all things in the directory. Notice that there's two guys that will always be there in every directory. That's dot and dot dot. So these are specially linked to dot being this folder, dot dot being the guy right above me. So the guy right above me would be the /users folder. So if I said ls-a ... that shows me in the /users folder. Okay, so this is just command line Unix gymnastics stuff. Okay, so one of the things, let's see, can I make this any bigger? Oop. So one of the things they're talking about here is they use a header file, tlpi header.h. And if you look in here, it has a whole bunch of systems already built into it. So they talk about a common header file. So for the projects for this book, or the sample code in this book, they've effectively created, I don't think this is a built-in header file, I think this is something they want you to create, but I'm not 100% positive. But if you look in here, these are things that already exist. So sys/types.h, standard io.h, we just saw that, standard library.h, the Unix standard for system calls, the error codes, string.h, and then get num.h. This looks like it's their function. So I wonder where that actually came from. I guess we'll keep going down the rabbit hole and find out. We might have to build this ourselves or something along those lines, because I don't think up here they told us where it came from. Yeah, they don't. So let's just keep going down the rabbit hole and see what happens. All right, so just looking at these types.h, type definitions used by many programs. So this is going to be things like standard types, like, well, I guess, we'll have int, long, char, things like that. And then we have some special struct types for like memory addresses, things like that. Standard IO has our IO functions, writing stuff out, reading stuff in. Standard library, prototypes of commonly used library functions, plus exit success and exit failure constants. Exit success is an integer that's usually 0. Exit failure is an integer that's usually 1, but is considered to be non-zero. Here's the Unix system calls, standard library. So this is the prototype for many system calls. This is effectively our Posix API. Here's error constants for different error codes. Here's a string handling function, because strings are actually difficult in historic C. We just saw our main program out there, or the main function. We had a char pointer argv, which was a array. It's a character pointer array that pointed to a bunch of character pointer arrays, where each character pointer array was a string, and we had a collection of those strings. Punchline is strings are kind of complex in C. So the string.h provides us a helper, kind of a wrapper class, if you will, for working with character pointers as if they're strings. Make sense? Because we're used to working with strings in Java and stuff like that, which have all these friendly functions built into them. Remember, C is a procedural language. So first of all, strings are not objects, so we can't say something.length. But secondarily, if we want to operate on character pointers as if they're strings, we have to have a whole bunch of functions for asking what's the length of this string, reversing this string, getting a character for a particular position in that string, stuff like that, things that we're used to just being available to us in Java. Well, C doesn't have those built in, so we can either write our own, or we can use string.h, which was later introduced into the standard template library and is part of the Posix standard, which gives us convenience functions for working with char pointers as strings. Okay? And then this get num thing, I'm guessing that's a function they write later on for dealing with integers and longs. Probably this is going to be in conjunction with standard IO. When we read something in from the user, we'll use a function called scanf, and things will usually come in as a as a generic void pointer format. So this must be a convenience for specifically asking for an integer, and it automatically typecasts it to an int, and so on and so forth. I guess we'll see where they go with that here in a few minutes. Okay, it's an error handling function. We don't do error handling, so let's forget about that. we wouldn't be much of a programmer if our code had errors in it.
Right.
All right. Oh, it doesn't flush. Oh, this is actually kind of interesting. We'll talk about it when we actually see it happen. Skip that. Let's get to something useful. Oh, here's a bunch of error names that exist in the errors.h. Oh, here's their here's an example of prototyping. So here is their file that they're writing code in that's including the TLPI header.h, which I assume is their file. I'm not familiar with that at the very least if it's not. And then they're prototyping two functions. One's called getInt, one's called getLong. GetInt takes in a string, so this char pointer arg is effectively saying a string. Then any flags, and then the name. So why is this guy taking in two different strings? I wonder how it's using name here. So it's converting this string into an int, and this one's converting this string into a long. I'm not sure what name is used. Or it doesn't contain a valid integer string. It's an error message and terminates the program. Oh, so this is actually the char. This name is a duplicate of this to be used in any error messages. It says should contain a string identifier. The argument in arg. This string is included as part of any error message displayed by these functions.
Is it included like this is what it was supposed to be?
How is this guy supposed to know what it's supposed to be?
Like, so if you're passing it an argument, so some number, and then the name, say you know that it's supposed to be a distance or something like that.
Name argument is non-null, so if it's something, it should contain a string identifying the argument in arg. So maybe it's not actually the argument, maybe it's just a information about that argument.
Yeah.
So what you're saying is, like, for example, if it took in a string that's supposed to be a temperature and it couldn't turn that into an int, it would print out that such and such is not a temperature. So name would be temperature or something like that. Flag arguments provide some control over the operation of the getInt and getLong functions. These functions expect strings containing signed decimal integers. All right, so to really understand the parameters for flags, we'll actually have to see the implementation of this guy to see how he uses these. Similarly would be true for this. So kind of what we're looking at here is the history of prototyping a header or prototyping a function. We don't see how these parameters are being used here. We just see that there happens to be a function named getInt that returns an int and takes these three parameters and it does something with them. All right, so we'd have to see the implementation later on to see how it's using those different things. All right. All right, here are the actual functions here. So both of them are written in terms of this getNum function. So getLong takes in the parameters we already expected, then it calls getNum, passing it the string getLong. So that's what we want to do to getNum. The argument, the flags, and the name. So here's getLong here. So it's asking what's the function name that you want us to call? What's the thing I'm converting? Any flags, and that error message name thing. So this guy comes in here and it asks whether arg is null or the just the carriage return. So this is the empty string. Nothing to convert in the empty string. So if this is true, then we'll go ahead and say null or empty string, and that prints something out. This is another function they wrote, gnFail. It must be up here somewhere. Here it is, gnFail. So this guy takes in function, message, blah, 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 prints some crap out to the screen. This is fprintf, so this is a file printf, and it prints out. So this is actually an interesting look into how Unix treats everything as a file. So fprintf is how we write things out to a file, specifically. You saw my Hello World program, which printed out, which just used printf, right? Printf by default prints the standard output. Well, notice here I'm using file printf, fprintf. I'm telling it where I want to print. So I'm specifically saying print this message out to standard error. Why would I choose to print something out to standard error rather than just let it default to standard output?
Error catching.
Okay, so like logging and stuff, we've even seen, we did some redirection stuff either last class or the class before that, where we were able to redirect output stream 2 to a file, where the standard output still came out, output stream 1 came out to the screen, but any errors that were in there came out into a file, and vice versa, right? If we had an error and we redirected standard output, output stream 1, so that's the 1 greater than sign, it would take all the contents and put it into the whatever file you directed, anything that would have been in normal standard output, but errors would still show up on the screen. So this is specifying that I want to print out specifically to this stream, this file descriptor. So let's not call it a stream here, because we've talked about in Posix operating systems, everything is a file. And we talked about a couple classes ago that specifically there are 3 file descriptors that exist right off the bat. Right? We have standard in, standard out, standard error. 3 different output streams, 3 different file descriptors that translate into an output stream right off the bat. So we're saying print to this file. What file? This guy. That guy's going to boil down to the file descriptor 2. That's the integer associated with standard error. What am I going to print? This message, where %s is a placeholder. This is a placeholder for a string. And I'll put in fname, whatever, where was that guy? This guy. That's the thing that I'm printing out. So that's the looks like a title for the error message maybe. Okay. Then if name is not equal to null, then we'll go ahead and print out the standard error again in whatever the name was. Then we'll put in the name. Print out the standard error again, the message. What's that guy do right there? Yeah, so that's artificially kicking this down a line. We saw when I ran my Hello World program out here, it put it all on one line. See Hello World right here? And that's because I never tell it to go down to another line. So now if I tell it to kick down the line and I compile it again, now it's on its own line. Okay, so that does our carriage return stuff. All right, so we'll print out the message that we passed into this guy. If our argument is not equal to null and our argument is not the empty string, we'll go ahead and print out the standard error again, whatever the offending text is, with a bunch of spaces out in front of it just to make it extra scary, I guess. And then we give it the argument. So they'll show us like, hey, you tried to convert hello world to a long. This is the offending text. Hello world. Bad news bears. All right, and then we call exit using one of the constants that was brought in from our error.h, which is probably, oh, here it is actually, error number.h. So this has in it these constants, and one of them is exit failure, which probably translates to a 1 or would be my guess, but the punchline is by using a constant, we don't have to worry what the actual number is, as long as the rest of the system always uses, if exit was failure, then do this stuff. All right, so this is what we do when we fail. This is the generic function that handles all of our things that leverages, that get long and get int leverages. These guys just call get num, passing it a different string. First one passes in the string saying get long from this guy. The other one passes in the string get int from this guy. So this function right here takes in the function you want to call get long or get int. This is our error stuff, so we call it gnfail. Otherwise, let's figure out base. So this is going to be looking at these flags. So here's an interesting question, trivia stuff from Java. What does that mean? Single ampersand. I don't think you have. You're also seeing here, so we'll come back to the single ampersand here. What is, I guess we're double dipping here, I guess. What's this syntax right here? What's this thing we're doing here? Yeah, it is a question mark. Yeah, that's what the symbol is. Go ahead. It's an inline if statement. Yep. So here, and several of you have seen me use inline if statements before, right? Where you have Boolean expression, question mark, what to do if it's true, colon, what to do if it's false. That's an inline if statement. So we're seeing that in action here. Yeah, there's 3. So if this is true, do this. Otherwise, if this is true, just randomly return 8. Oh, if it's base 8, I get it. Why am I returning 8? Okay, so if flags was provided and we're in any base, except we're gonna come back to this. It's a very special kind of and, so now I've given you a hint. Then we'll return 0. If it's base 8, return 8. If it's base 16, return 16. Otherwise, return 10. So this is anything else. If it's any other base other than 8, 16, or 10, return a 0, kind of like, I don't know what to do with this. It was in base frog, so we're not working with that. But if it's 8, 16, or 10, we'll handle that. So anybody remember what the single ampersand is used for? Java supports this as well. Go ahead. Oh, it is Bitwise. What does that mean? Did you look that up, or just somewhere in your mind there was this phrase Bitwise and you thought that might be right?
No, I didn't look it up, but I just know that single ampersand is Bitwise.
Okay.
It says use like all the others, like or as well.
Yeah, so this is the Bitwise AND versus the Bitwise OR versus the Bitwise XOR, which is just the caret.
Because he's the doctor.
All right, so we have half the answer. We have the description. This is the bitwise AND operator. What does that mean? It's pretty common to be used with things, I guess, called flags. I don't really know the nature of what their flags look like here, so we're playing with a little bit of fire, but I'll show you as an example. So bitwise. So let's say we had 1101.
It compares each bit of the first operand to the stuff in the other one.
Yep, to 0101. So you look at it. Look that up.
No, it just took a little while for it to reach the top.
Journaling file system. I had a burrito for lunch. Isn't that weird how that strangely made some sense? All right, so what a bitwise AND does is instead of taking this entire value and ANDing it against another entire value, obviously these are just bits, right? It takes this 1 and ANDs it against this 1. So 1 and 1 is 1. 0 and 0 is 0. 1 and 0 is 1. 1 and 0 is 0. So that's like true and false. All right. So this guy would boil down to 0, 1, 0, 1. So if I did a bitwise AND between these two numbers, I get 0, 1, 0, 1. Make sense? So, and this is something we talked about. Actually, didn't we talk about this quite a bit in the computer organization class? 325?
Oh, that's next.
Oh, you haven't had it yet?
No.
Who in here has had that class? Why didn't you all have your hands up on this bitwise stuff? No. Did you really have a burrito for lunch? Are you serious? Or now you're just lying, you're just playing along with the story?
No.
From where?
God, you're fat. What kind?
I know. Double chicken,
What queso?
regular.
Don't they have
One
bacon?
scoop of Diablo and one scoop of Pepper. That's the only way.
What's wrong with you? Don't they have bacon queso?
Nuh-uh.
If they don't have it all the time, they had it.
I believe it was specialty. I don't
That
know.
might have been it. Because I remember one time I went in there and I was getting. My wife doesn't want any of the queso because even the mild, has too much spice. Yeah. My wife thinks ketchup's spicy. Well, she doesn't like ketchup to begin with. I think she doesn't like it for other reasons. But yeah, she does not like spice at all. But I figured when they said bacon queso, just because of that and knowing I couldn't put it on hers, I ordered a burrito. So I usually just go there and get it for her because it's usually off my diet. But that ship has sailed. I just stopped trying in the winter. It's so easy during the summer when I'm golfing all the time or fishing all the time. But now I just sit around. There's just food everywhere. You got to operate out of convenience.
I think you need to get heavier in the winter. I think it's acceptable.
It's like a bear thing.
Yeah, exactly.
Yeah.
You're
I've been looking for a place to hibernate. Can't decide between my massage chair or the hot tub or just the couch. So I'm kind of bouncing back and forth between those options. My wife keeps saying, well, why are you bulking up for that? Well, I say, I usually keep a bucket of M&Ms nearby just in case I get desperate. Actually, it gets even worse than this. I just saw them in the store the other day. I bought a package. They have these giant M&Ms. Have you seen these?
Yeah.
It's like 7 or 8 M&Ms in one M&M.
But if you do the math, you're getting kind of ripped off, I think.
It doesn't matter. They're awesome giant M&Ms. So I don't have to chew as much. I can conserve energy. I'm only having to get through one shell.
But you have to chew. You could just swallow the little ones whole.
That would be pretty funny. Somebody's eating M&Ms like they're taking pills.
Doing vacuum lines of M&Ms.
Add some M&Ms to daily pills.
What are you doing? Doctor says I need to have 5 M&Ms a day.
M&M or a Skittle?
2 M&Ms, 1 Skittle.
Remember the big one from Rapid Starburst?
Seriously, I was just thinking that. That actually reminds me of another interesting. I think it's sort of a bathroom related story.
Maybe use Mica because they're more like pills anyway.
No, so this was years and years and years ago. But I was having some stomach problems. I went in and I had the doctor, and they went to do all these tests and stuff. So they give you this this kit. They said the nurse calls me up because I had just been sick for multiple days. She says, "Oh yeah, you need to come by and you need to pick up this bag prep kit." I'm like, "Okay, well, what's that?" She's like, "I'm not really sure." So the nurse calls me and says, "I need to go pick up this kit that I need to take before the next day." And couldn't tell me what it is. Well, it's a nice suite of laxatives and pills and stuff like that. But inside this thing was like pills you're supposed to take and then pills you're supposed to put someplace else. All right. Well, and that one's obviously a much larger one. So the next day when I go in, I'm joking around with the nurses at the thing. I said, you know, the little ones were easy, but that big horse pill was impossible to swallow. And they thought I was serious. You just got what the horse pill is now, didn't you? Yeah. It's the whole burrito. It's the burrito thing, journaling file system. I get it.
So it's like they're showing commercials now for this like medical service where it's like they send you a box, and you crap in the box, and you send it off.
Yeah.
I did that last
You have
year.
cancer.
Oh yeah, when I went to my shaman last year, he sent me home with all sorts of different home tests I had to do. So I had one of those boxes. My poor wife. What was I talking about? Oh, Bitwise. Yeah, so this is a Bitwise operator. So they're taking whatever these flags are. They're doing Bitwise and with whatever this constant is. So this constant is from one of the header libraries. If that guy turns out to be true, which would be all ones, so more than likely these are single bits, would be my guess. Okay, but if it turned out to be all ones, then it would go down to a 0, so on and so forth.
Why wouldn't you use just a regular operator, just a double ampersand?
Because flags are an int. Double ampersand is for comparing booleans. Make sense? So, and really, what you're saying is correct by today's thinking. You got to imagine that we're looking at kind of the old way of programming. This is kind of the Posix way of doing things. So things are going to kind of seem a little weird, but hopefully as we're kind of peeling back the layers, even though we don't really know the nature of these flags yet, it makes sense what's going on here. It's not that hard to follow, but at a glance, it looks intimidating, right? It kind of looks like weird code when we first look at it. All right, so if what they gave you didn't have stuff in it, yell at them. Otherwise, figure out what the base is. Then, initialize your error number to nothing. So far, so good. All right, then we're going to go in here, and this takes the string too long. All right, that's this built-in math library, and this is part of the POSIX standard. So this converts a string to a long, giving it the arg, giving it the address of the end pointer. Where does end pointer? So here's the char pointer for end pointer. Do we ever give this guy a value? We don't. So this is actually the address of this variable. Not the address the variable holds, but the address of that variable. So this guy, when we call string to long, we're passing it the thing we want to convert to a long, along with the memory location where we would like it to put the answer. That make sense? So here's a variable. I'm not going to give you the variable. Instead, I'm going to tell you the address that variable not points to, the address of that variable. So here's the address where I want you to put the answer. And then here's the base that you should do your thing. So string to long takes in a string, takes in the base that string is being represented in, and takes in the address where the answer should be put. All right, so this is kind of along those lines of what we saw with the assembly code last time. We're like staging things, and we know where to go to look for the answer, that kind of stuff. Go ahead.
Is sending it the address, is that defined by the ampersand?
Yes. So here, go back here real quick. I thought I had done this stuff in here. Did I? Didn't I show you the syntax for pointers and addresses, or were you just not listening? I didn't do it in here? Okay. All right, so let's say I have an int a is equal to 5. Int star b is equal to the address of a. Then we'll print out a is equal to %d. Address is %p ab. So I'm going to print out, let me do a carriage return too so it kicks it down the line. So I'm going to do a print statement here. So this is essentially how C does concatenation. Okay, we do little placeholders in here. So I'm going to say A is equal to, this is a decimal placeholder. And that guy's going to get replaced by whatever the value of A is. The value of A is 5. And then I'm going to say the address is %P. This is the pointer placeholder. And that's going to have B put into it. What's B? B is an integer pointer. So this is the syntax for defining something as a pointer. That is a variable built for holding a memory address. So B is a variable built for holding the address of an integer. That make sense? That's the kind of value that B holds. Not an int, but the address of an int. All right? There's nothing special about that. Every single variable we ever create is the type that's built to hold, the name of the variable, the value that goes in here. The type this guy is built to hold is an integer pointer. It's built to hold the address of an int. Its name is B. The value is, this is the address of A. Make sense? So this should print out 5, then address is weird address. I won't say weird address, it'll look like a weird address. That was mostly for your benefit, Evan. So there is 5, and there's weird address. Make sense? But now we're not seeing virtual machine addresses, we're seeing actual real memory addresses. Remember virtual machine addresses, they look weird, but it's like at whatever, Java makes it look like you kind of know what the thing is. This is just completely random memory. All right. All right, so we'll go ahead and get our result. So our result is a long. So the result will be whatever's returned by string to long, arg, end pointer, and base. So how are they using end pointer here? Because this thing is returning the value. So this is going to be the int. We'll have to see what end pointer is actually for. They're not storing the answer there. They're storing something there, but not the answer there. It might be the last, how long it is in memory. Guess maybe we'll stumble on it. Something bad happened, print it out. And if another thing bad happened, print it out. So this is, the thing just failed. We have non-numeric characters. This is, you're not allowed to convert negative values. I don't know why. It must be that string to long doesn't allow that. Value must be greater than 0, so kind of the same thing. Otherwise, we'll return the result. And this guy returns a long. Now, what's interesting here, actually. Oh, yeah, here he does the extra work in there. So why is it that get long, do we ever use fname in here? Oh, yeah, they just use it for an error message, that fname. Because both down here, get long and get int, both use get num. Get long passes get num, get long. Get num passes, or get int passes get num, get int. And those guys aren't used for any sort of like if statement or anything inside of the get num. They're just used strictly for if there's an error message to say what it was trying to do. Because get num 100% of the time returns a long. That guy returns a long. So if we're in our get long function, we just call get num and return the answer. But if we're in the get int function, we go ahead and get our answer. Then we make sure that it's not too big for an int. So if the result is larger than int max or the result is smaller than int min, then do the get fail, get int, out of range, blah, blah, blah. Otherwise, go ahead and cast it to an int and return it. Make sense? So just some introduction C type stuff. All right, so this is talking about the portability issue, and that's one of the things we might bump into with doing this on the Mac. That's why I did a Cloud9 account. We'll look at that just in case. We'll try it on both. Let's go down here. All right, so here's a couple of interesting things. This is talking about data types. This is for SUSE Linux. So if you remember, way back when we were looking at Java, we talked about like how big's a byte, how big's a short, how big's a int, long, so on and so forth in terms of bytes and stuff. So this is going through all of these different data types. So we have a file block count, a file block size. So each of these is a data type, but most of these are some twist on an integer. So this is a signed integer, an unsigned integer, integer or real float, so on and so forth. Okay, notice that certain ones of these are 32-bit or 16-bit as opposed to the system generic integer size, whatever that is. So it might be, on a newer system, it might be a 64-bit int default, so on and so forth. All right, so that gives us some of our bases. So we'll come back next time. We'll start on 66 at the bottom and start looking at some of the struct stuff. And hopefully we can start writing something here pretty soon. So for homework, get caught up. I would read everything from up to the end of chapter 3 here. All right, because we'll be starting. We'll probably look at the exercise 3.1 in class, and then we'll start file I/O stuff on chapter 4. There might be a quiz involving that reading.